Hi, everyone. Thank you for coming to our industry talk. My name is Matt Cousins, and I work in the education team at Arm, and I'm joined by my colleague Kieran Hajmadi. And we're going to be talking about KleidiAI and how that is used on Arm Neoverse platforms in the cloud to scale AI deployments. So, first thing to talk about really is the new era of computing infrastructure that we're in. It's widely understood by everyone that we are, of course, in the age of AI. And some of the key trends that are driving this are data proliferation, sustainability concerns, and the fact that Moore's law can't keep up. So data proliferation, well, global data usage reached 175 zettabytes by 2025. And of course, it has gone on to exceed that. And this data usage that we generate as a civilization and the ways in which we process this data using AI and machine learning are expected to accelerate going forwards. So there is both a need, a demand, and an opportunity for infrastructure that can support this. But there is a concern with sustainability. Infrastructure currently consumes 3% of global energy, and it's important going forwards that infrastructure directed towards AI is as power efficient and sustainable as possible. Because not only do we have concerns in terms of the amount of power we're using, because it can be negative for the environment, but also because there are logistical concerns with cooling data centers and cost concerns for those operating the data centers as well. So having very power efficient processors is vital. And then the final trend, the fact that Moore's law can't keep up. So Moore's law is the observation of the number of transistors in chips doubling roughly every 2 years, whilst the cost per transistor went down. And this meant that we gained an exponential increase in compute power, whilst computers also became more affordable. And of course, that led to computing pervading every aspect of our daily lives as they became very powerful and very accessible and affordable. So because Moore's law isn't keeping up, we need to look for new ways for how we can adapt hardware to support AI going forwards. So more than 50% of established data center capacity is dedicated for AI training and inference. So where we have cloud and data centers, a significant majority of that is being used for AI. And again, we expect this to increase. So previously, a lot of the narrative around AI has been about training, but training is just the tip of the iceberg, with around 15 to 20% of total AI workloads being training. And this is typically run on GPUs or TPUs, tensor processing units. But going forwards, the growth is actually going to be in inference. So training is where you teach your model and it gets very good at the task that it's trying to perform. But inference is actually when you execute that model. You already have a well-trained model and now you're going to use it. So every time you're using a service like ChatGPT, that model has already been trained and you are using that model to infer based on the prompt that you give it. So you are completing an inference operation. And going forward, we're expecting this to be around 80 to 85% of total AI workloads, which is the significant majority of the workloads, and therefore where our focus is going forwards. And it's key that this is done at low total cost of ownership. So for the people running this hardware, it has to be cost effective, and again, it also has to be power efficient. And it has to do this at scale, because these data center deployments are massive, and small improvements can have a significant effect when scaled up. So some other trends that we're seeing, LLMs are getting smaller and they're getting more specialized. And I'll look at some examples shortly, but fine-tuned domain-specific LLMs are expected to be the key going forward to solving specific challenges. And the techniques that we're using for inferencing in AI are getting more efficient, And crucially, CPUs are getting better at inferencing. So we're no longer stuck in the paradigm where we have to use GPUs or TPUs for all of our AI workloads, but rather CPUs, which are already ubiquitous across all sorts of devices, whether it's in the cloud or the edge, are now being able to be used for inferencing going forwards. So here are a few examples of some fine-tuned and domain-specific models and how their performance compares against more generalized models. So the key thing is that these models are significantly smaller. We don't exactly know how many parameters the latest versions of GPT, GPT-4 and GPT-5 use, but it's widely understood to be in the hundreds of billions and possibly over the 1 trillion parameter mark. Whereas with significantly smaller models, some examples here have 70 billion or 13 billion, we're able to achieve similar or better performance. So in the domain of healthcare, the Hippocratic AI with a 70 billion model is achieving a greater performance than GPT-4, which is widely understood to be a much larger model, and actually achieves slightly greater accuracy than a current registered nurse in the US. So this is the sort of performance that we would want, because obviously medical and healthcare, it is vital that you're getting the most accurate assessment. And we're able to do this with a much smaller model that has been focused towards this. And we see similar trend in the domain of finance and also in software development and code generation as well, where focusing in on these models and specifically training them on key information, as you might expect, makes them better at those areas and doesn't require massive parameter models, which in turn would require a lot more compute power to be able to run. So it's a lot more feasible to run these sorts of models on CPU systems. And there was a quote there from Sam Altman, CEO of OpenAI, who agrees that actually it's domain-specific, fine-tuned models that are going to be the future. So when we're running these models on CPUs in the cloud, there are a few techniques that we can use, and one of those is quantization. So this is an optimization technique where we reduce the precision of the parameters that we're using for the model. So a typical model, when it's being trained, they might use floating point 32, FP32, which is just a format in which the data is stored. But we can actually reduce that precision considerably to first perhaps floating point 16, then maybe floating point 8, and even dropping the floating point and moving to an integer format with int 8 and int 4, as this requires a lot less compute power to handle. But the key thing is that the trade-off when it comes to quality is relatively insignificant. So you have significantly improved the speed at which you can process it, or reduced the compute power required for this model, but the quality has not noticeably degraded. So this particular graph shows that comparing int 4 with floating point 16, we get roughly 3 times smaller, which is great, but it is also 2 times faster, and we still have 99% of the original quality. So that is a clear and obvious win. So how is Arm addressing this? The fact that there is this opportunity here where we need power efficient processors. There is the opportunity for CPUs now to be running smaller and more domain specific models, and perhaps models that have undergone quantization to make them fit on other systems and make them be able to be run easier. Well, Arm is deployed in the cloud through its Neoverse IP and Neoverse compute subsystem. And you can see some of the companies here that use the Arm Neoverse as a foundation for their cloud services. So it is very prevalent. So I mentioned Neoverse IP and the Neoverse compute subsystems. So the Neoverse IP is a processor core designed for cloud and server deployments. And this has been very effectively utilized in the cloud for CPU inferencing. But increasingly, we are providing IP as part of what we call a compute subsystem, or CSS. And this provides a validated, performance optimized, and integrated subsystem that allows for the fastest path to production silicon. So this essentially means that this has been worked on by Arm, integrated with other bits of IP, and it's far easier for our partners to take the compute subsystem and then make the adjustments they need, and then work with a foundry to tape out their chip. And ultimately, the Neoverse V1 is the best in class for the total cost of ownership for on-CPU LLM inferencing. So this means that compared with other alternatives on the market, it is far more effective for people to adopt Neoverse for scaling their AI deployments in the cloud. So Arm Neoverse has been optimized in hardware for AI. So it has various features that allow it to support running AI models. So for example, it supports the BrainFloat 16 format, and it has various instructions that speed up common operations used for AI models, so matrix multiplication and vector operations as well. And this means that it is able to run these models much more effectively. But the key topic for today's talk is something called KleidiAI, and this is targeting more of the software space. So today's AI and machine learning software stack is relatively complicated in some ways and has several layers. So you would have the end user applications, and these will utilize models. And these models will typically be written in various frameworks. It could be PyTorch, TensorFlow, or Onyx, and many others as well. But how do these frameworks actually interact with the hardware? Well, that's where the Kleidi technology comes in, and it provides that bridge between the hardware and between the commonly used frameworks. So this is a library, essentially, or a collection of libraries that provide, again, pre-optimized microkernels, which are essentially routines where if you run a typical function from an API in one of these frameworks, whether it be PyTorch or TensorFlow, then Arm has already provided the best way for the hardware to be used to achieve that function. Because normally in software, a function could be compiled down into several different ways of actually being executed, whereas these have been designed to be the best, the most efficient and fastest ways of doing it. And these will run across all frameworks without requiring the end user to actually understand that they are using the ARM technology underneath, and is very seamlessly integrated. So you can see here some of the typical frameworks that I described automatically feed into the Arm Kleidi technology, and then are able to run the models and make applications that utilize AI work far more effectively. I'll now hand over to Kieran, who's going to talk a little bit more about PyTorch inference using KleidiAI, and also show some demos as well.
Thanks, Matt. I'm just going to quickly share my screen. I hope you can see my screen clearly. So how does KleidiAI actually integrate into one of these frameworks? So Matt showed previously that a lot of frameworks like TensorFlow and PyTorch have this integration. So let's take PyTorch as an example. So most developers are used to using high-level APIs. For example, if you're writing a recommendation system, there'll be an API to perhaps have an LSTM layer available through PyTorch. But of course, anyone who's ever touched machine learning realizes quickly that a lot of this is just matrix multiplication. And as an example, PyTorch has a general library called A10, which stands for a tensor library. And to support a variety of backends, traditionally there's been a lot of abstraction layers. For example, there's the 1DNN that might be able to find an ARM compute backend, or it may even look for other devices such as GPUs from Intel or NVIDIA. But KleidiAI is integrated directly into this A10 layer, so it is able to bypass the layers of abstraction and go straight to the CPU features. So at the bottom here, we have an example from AWS Graviton, which are cloud-based instances based on the Neoverse architecture. And these have a variety of CPU extensions that Matt showed earlier, such as BrainFloat 16 and i8mm, which is 8-bit integer matrix multiplication. And PyTorch is able to automatically find what features are available and delegate the right microkernel to run. So this is all transparent to the developer, and actually they can directly use these high-level APIs and benefit from the performance increases. So what is the performance increase? I've spoken a lot about this backend, but how fast is it? So on the left here, we have a graph of PyTorch by default, and this is without the Kleidi support, which was added from version 2.5 onwards. And in green, we have PyTorch with that KleidiAI backend. So Matt talked about quantization. What we've done here is taken the Llama 2 7 billion parameter model, and we've quantized it from the default level of precision, which is 32 bits, down to int 4, so 4 bits. And as Matt showed earlier, this has a very small reduction in accuracy. But by combining quantization with KleidiAI, you're able to see that we've have a significant increase in the generation rate in tokens per second. And it's really surprising how fast these small kernels can be. These examples of the Gemma model, which is Google's open source model, the 2 billion parameter version saw a huge increase, 14 times uplift. And this data is taken from an AWS Graviton 3 based on the Neoverse V1 architecture. And it's using a 16x large instance, so not a huge CPU-based system. So to kind of visualize what this looks like, on the left, we have without the KleidiAI backend support, and you're getting 13 tokens per second. It generates the text quicker than you can read, but actually it takes a while for it to get to the answer. And in the age where we have reasoning models where they kind of speak to themselves, there's a strong need for a fast token generation rate. And it's incredible to see how quickly just a CPU-based system is able to work, generating nearly 70 tokens per second in the decode phase. Just going to pause it here. So actually earlier today, I wanted to see what it was like. So I took a Neoverse V2, which is an AWS Graviton instance, and I ran the 1 billion parameter tiny llama model. And I was using a recent version of PyTorch. And I'm using this in the eager execution mode. So this is Python running similar to an interpreter without compiling ahead of time. And I asked the question, what's the meaning of life? I had a few high-level parameters, so I set the number of threads to be 16. You can generally ignore all the kind of warnings here, but you can see it was able to answer. It gave us a Mark Twain quote. I'm not sure how accurate this quote is, but I think it's a good answer to the meaning of life. It's also able to show some more detailed information. So not just the tokens per second, but breaking it down into the pre-fill tokens, which are when your prompt is being processed, and the actual decode phase, which is generating new tokens. And it's amazing to see that nearly 250 tokens per second are being processed in this pre-fill phase. And this is with running 16 threads on an AWS instance. Right. So if you'd like to have a go for yourself and see what performance you could get, there's a variety of ARM-based systems. You could try it on a Raspberry Pi. You could try it on an AWS instance. You can even try it on an ARM-based laptop. We have a collection of tutorials available on learn.arm, and there's a link here if you want to try it yourself. And this is running PyTorch and ARM-based servers using the Llama 3.1 model. And this is a really easy way. You copy commands and paste them into your system. And within, in this example, 30 minutes, you can have a chatbot running on an ARM-based CPU. So it's not just chatbots and large language models. Of course, matrix multiplication is used in a variety of AI applications. And KleidiAI accelerates general matrix multiplications. So it could be automatic speech recognition for applications such as Siri, recommendation systems. Many of these applications will have microkernels from Kleidi. And there's plenty of resources to get started. You could look at the official documentation on PyTorch, or you could go to our own website and see the Kleidi announcements. And there's a variety of blogs looking at different models and how they perform on different architectures. But if you want to get more practical, there's a variety of learning paths. These are our tutorials around running chatbots and RAG-based systems on Kleidi. And for those of you within academia or generally looking to learn, we have free and open courses on edX. So we have a course that was released earlier in this summer on optimizing generative AI on ARM processors, and that would apply from edge devices to cloud, which goes in more detail about KleidiAI. It compares it against open source alternatives such as OpenBLAS, and you can see the performance there. A new platform called Arm Developer Labs. So this is a collection of industrially relevant projects that you could do perhaps as research or part of your curriculum for practical labs. So I'm going to quickly bring it up here. So Arm Developer Labs is available on GitHub, and we have the URL here. So we work with a variety of software partners, for example, MathWorks, Linaro, and Arduino, as well as academic institutions, for example, Anglia Ruskin University in Cambridge. And we work with them to find projects that are relevant to the ecosystem as well as academia. So if you navigate to the projects tab, you'll see we have a variety of projects, and these could span cloud AI, but it could also be machine learning for mobile devices or other platforms. So if I'm just going to quickly use the ML filter. So you can see we have ML challenges for AWS Graviton. And in this example, it's all about text to video or running on CPU systems. And through this, we provide resources to get started, for example, tutorials on getting started with AI, as well as blogs and repositories for references. And this is a collection of projects that are really exciting to do. They're industrially relevant. But as I said, it's not exclusively cloud-based AI projects. We also have projects around mobile devices. For example, we recently had one on neural graphics. And if you'd like to learn more, please go to Arm Developer Labs and check it out. And I actually want to give you a sneak peek of some of the future content that will be available shortly. So in a few weeks' time, we'll have more advanced AI content. This is going beyond the traditional quantization or reducing precision, but actually to advanced techniques. So how could I train a model to be aware of the quantization? And how far can I take this quantization? We currently showed 4 bits, but could I go down to 2 bits? And this resource is a collection of Jupyter notebooks that take you through that. So in a few weeks, if you go to the ARM Education GitHub channel, you'll see the course available there. And this is finally just for all our resources from the ARM Education team. We have our edX courses where we have our AI courses, as well as other technologies. We have our resources for general developers on learn.arm and Developer Hub. as well as our developer program, where you can get technical support for questions and communicate with a community that are interested in ARM-based technology. For those of you looking at taping out and designing chips, we also have the ARM Academic Access Program. And there's the flyer here, and you can scan the link or visit the URL here, where academia can get access to ARM IP to potentially tape out chips. And we have a community of practice to support universities in taping out called SOC Labs. And we have a QR code down here. And finally, if you're interested in stretching yourself in terms of software challenges, or if you're in a teaching capacity looking to work with students as part of maybe a design project, please visit DevLabs to see a collection of industrially relevant projects.
So at the start of the presentation, I shared about how the trend with AI really is that move from training to inferencing. And that's happening both at the cloud and the edge, but AI at the moment largely is popularized at the cloud. So that trend to inferencing requires a more versatile device than your typical GPU and TPU. And of course, the other clear trend was the fact that LLMs themselves are getting smaller and they're getting more fine-tuned. And this actually just makes it easier for us to use CPU devices to run these models instead. And then finally, the fact that we have techniques to optimize these models for more constrained or lower compute devices like CPUs, using techniques such as quantization, again, just helps and is another trend that supports this trajectory. And to support that, ARM provides the Neoverse platform, both as IP and compute subsystem, and has integrated that with all of the main existing frameworks for machine learning, whether that be PyTorch and TensorFlow. And of course, Kieran has then very aptly demonstrated the speed up that you can get by running a model using KleidiAI on PyTorch, and the significant difference when not using KleidiAI as opposed to using it. And this is very important for improving inferencing on CPUs going forwards.